So in this video, we're going to cover how to use tabular integration for circular problems, as well as for other problems that don't sort of follow the original pattern of the first video that we had. So we're going to get right into the examples. So here it is. Hopefully you recognize that this is definitely one of those circular problems. We know that it is because there's an e to the x, and there's a sine or a cosine. They pretty much always look like that, right? So it's tabular integration. I set it up exactly the same way. I make my table, I have my derivative side, and I have my integral side. So now we have to choose, what do we want to take the derivatives of, what do we want to take integrals of? I addressed this in the previous video. I want you to pause and see if you sort of recognize which you want to put where. I really believe that we should do our sine of 3x over here, because derivatives are going to give me like 3 and 9 and 27 multiplying by 3. If we put that one on the integral side, we'd end up with fractions. You will totally get the same answer. It's just going to happen through fractions instead of through whole numbers. On the integral side, therefore, we're going to be doing e to the x. So now, this is similar to tabular, but it's a little bit different. Because remember, with tabular, with the original tabular, what we did is we kept taking derivatives until we hit 0. Like, that was when we knew to stop. That's never going to happen here. So what we're going to do is we're going to take the derivative and the integral of each one and then sort of evaluate where we are. So first, the derivative is 3 cosine 3x. The integral of e to the x is e to the x. Okay? And we're supposed to put a negative on the outside of this thing. The question is, do you know how to do this integral? And what it comes down to is, if I were to stop here, if I were to stop here and, sort of do this diagonal and then add this integral, would I be able to do the straight across integral? The answer is no. I don't know how to deal with a cosine x and an e to the x. So we're going to go another step, right? Let's do another derivative of 3 cosine 3x, right? Another derivative of that would be negative 9 sine 3x. Okay, now I need to point out here, this negative here is like on the outside. It's not being considered in this thing. Only reason this is negative is because the derivative of cosine is negative. So then I do the integral of e to the x, and I get e to the x. What it means is, okay, I've decided I'm going to go diagonally one more time. And now you assess again, could you deal with that integral? And the answer is kind of no, but on the other hand, that integral right there is e to the x sine 3x, which is what I started with. Once you've done this, what we know is we know that our original integral, the integral of e to the x sine 3x dx, what is it equal to? And I hope you guys can read this from the table. What it's equal to is it's equal to e to the x sine 3x minus 3e to the x cosine 3x minus the integral. Why am I doing integral? I'm doing integral because on the third one I decided to go straight across, minus the integral of 9 e to the x sine x dx. And this is great because now this last piece can be added over. When it gets added over, I end up with 10 of those integrals, e to the x sine 3x dx, equals the pieces that weren't a part of that integral. So e to the x, and actually you can just factor out the e to the x right now, save ourselves some time, e to the x sine 3x minus 3 cosine 3x. And our final step is, I'm going to save us some time, final step is divide that 10 over, and of course, don't forget your plus c. So We absolutely could have done this problem using the exact same method we did before, where you just use integration by parts. And if you prefer to just use double integration by parts, if it's hard for you to follow what's happening in this table up here, where you have to choose when you're going to stop, then don't use Tabular to do these problems. I just wanted you to know that it's possible. So this problem is not a tabular, this is not a circular problem, but it is one that we might try to use tabular for. But anytime you have an integral involving natural log x, you're going to want to put that natural log on the, in fact we have to put that thing on the derivative side, because we don't know how to do the integral of natural log x. So I'll put my ln x here, and on the integral side I'll put my x cubed. And so this is not a circular problem, but I wanted you to see how it works with tabular. So what's the first step you would do using tabular here? Well, we would take the derivative of this side, and we would take the integral of the other side. Okay? Now, the way tabular sort of works is we say, okay, it's going to be this times this. Now, am I prepared to do this? By the way, we have to change this sign, don't forget about that. Am I prepared to take the integral going straight across? And the answer is, yeah, totally. Think about how nicely 1 over x and x to the fourth are going to play. Right? What I could do here is I could just say, okay, well, it's 1/4 x to the fourth ln x minus the integral of this times this, and whatever, that's just 1/4 x cubed dx. That's not even difficult, right? This is going to give me 1/4 x to the fourth ln x minus 1/16 x to the fourth plus c. And in some sense that could be enough. We could simplify it more. We could actually make it really pretty. If you were to factor out x to the fourth over 4, you'd end up with ln x minus 4. No, sorry, not 4. I suppose that would be 1/4, right? Because if you divided out, if you factored out the 1/4, you would need a 1/4 left there, plus c. But man, that's ugly. I want to pull out that 1/4 also. I guess it would be x to the fourth over 16 times 4 ln x minus 1. That business of factoring out fractions is something we sort of mentioned last year. If it's something that you're mathematically comfortable with, do it. It's a great tool to have and to know, but I'm not going to force it on you right now. So that's it for using tabular integration. That's sort of the end of integration by parts. It's a complicated method, but one that you definitely get better at with practice.